Hi everyone, my name's David Rowley and I'm a Postgres committer at Microsoft. And today I'm here to talk to you about what's new in the Postgres 18 query planner. And this talk's going to be useful for anyone who's thinking of upgrading to Postgres 18 when it's released later this year, or anyone who's thinking of migrating to Postgres and wants to check in on the latest features. Okay, so let's get started. So just a little bit about me before we start. So I've been working on Postgres for about 12 years now, full time. And for 6 of those years, I've been a Postgres committer. And so I mostly work on performance related features. Quite often that's inside the query planner itself, and sometimes more general performance improvements, and quite often maybe execution performance improvements. So if we get started. But first, a little caveat. So the Postgres feature freeze for 18, that started on the 8th of April, which for me, this is pre-recorded. That was 3 weeks ago. And what the feature freeze means is this is a point in time where we stop accepting new features into Postgres and we start to try and stabilize the release. And because that is not so long ago, it's possible that something changes between when I've recorded this and when the actual release is made, which is around September, October this year. So, yeah, with that caveat, it has happened before. And one of the features that I'm going to talk about today previously was in Postgres 17, I think, and did get reverted. So let's hope that doesn't happen, but it is possible that it does. So I'm going to break this down into two parts. And part one is just about what's changed, what smarts have been added to the query planner in Postgres 18. And then part two is more sort of general planner performance improvements, thing that it's not necessarily like a new smart that's been added to get the planner to produce some kind of plan that it didn't before. These are more sort of performance related things. So if we get started on part one, and just about the format that I'm going to use here, in each feature that I'm going to talk about, I have pasted details about the actual commit. So if you want to go ahead and get more details about this, then you could look up that commit number. And these commit messages are often quite long for these features. So I've had to truncate them off in pretty much all cases here because it doesn't fit on the slide. So there is more detail if you look these up. And also, the author, as it appears in the commit message, that is the committer, and quite often that differs from the actual author of the patch. And to highlight the actual authors, I've just put a little speech bubble on the left, so look out for that. If one is missing, then you can assume the person who committed it is the author. So for this particular feature, effectively, if you have a where clause and you have a condition like where column equals some value or the same column equals some other value, and you have an index on that column, that is now effectively converted into an in clause. And what this sort of fixes is quite often previous versions of Postgres would implement this OR clause by doing bitmap heap scans with a bitmap OR to join. And there'd be one of those effectively per value that you're looking up, per OR clause and branch effectively. And that could cause problems. If here I've only got two in this example on the top, but in theory you could have dozens or hundreds of these. And that would make the plan much bigger than it needs to be. And that would slow things down in terms of like executor startup and shutdown. And so this effectively helps resolve that problem. So if we go into a quick example here, and I'm creating a table called parts. This table is going to feature quite a bit through the talk. I've tried to be consistent and stick to this table so it's just easier to parse. And the things to note here are that there's a unique constraint on the part code. And the query that I'm going to run at the bottom here, if you look at the select star from parts where part code equals ABC123 or part code equals 123 ABC. And if we step forward and just look at how Here I've got the explain output, so I'm hoping you're comfortable with looking at that, but I'll try and just describe what is happening here. So in the top box, and this is the output of explain for Postgres 17. And you can see that at the bottom, we've effectively got two bitmap index scans. Effectively, it's scanning the same index twice. And if you're looking at the index condition, you can see our values that we're looking up, the ABC123 and the 123 ABC on the lower one. And then if you follow up, you can see the bitmap R. So that's effectively, it's generating a bitmap of the matching physical addresses of the tuple that it found during the index scan. Then it creates a union of those from each side. And then it does a bitmap heap scan on the actual part tables to find the actual tuples that exist in the heap. And that is suboptimal. So if you look at the bottom box in Postgres 18, it just does an index scan. And you can see that it's using equals to any, and then there's an array of values to search for. And that's going to be more efficient to execute. And it's going to be cheaper to start up that plan and shut down that plan, which is something that has to happen every time a plan is executed. So onto the next change, self-join elimination. So like, what is self-join elimination? Well, Postgres for quite a while now has had the ability to remove unused left joins from the query. And effectively, the place where that benefits probably the most, where it applies the most, is probably when views are being used. And you might have defined a view that joins a bunch of tables to get additional information, but maybe sometimes you use a subset of the columns from that view when you actually use it. It could well be that you don't necessarily always need to join those additional tables in all cases. And for a while now, Postgres has allowed this to happen for left joins. So this command for Postgres 18 effectively allows this for self joins. And this can apply when it applies when there is an equality condition joining the two tables. And that equality condition effectively has the same column on either side of the condition. And there's also some kind of unique index to ensure that duplicate rows don't, to ensure the join doesn't cause duplicate rows. So let's move on to a quick example. The parts table has returned. And here you can see, if you look at the query at the bottom, I'm joining the parts table to itself on the part ID. And so if we look at how that is executed by Postgres 17 and Postgres 18, on the left, I've got Postgres 17's output. And you can see, you don't have to look in detail, but you can see there's a join happening there, hash join in this case. And for Postgres 18, no joins, just a sequential scan. Effectively, the P1 has been completely removed from the plan. Just a little bit more about that. Like I have actually, it seems like who would write that query and who would do that? Like, why would you end up with a query with where the same table is joined multiple times? And I have seen it in the past where in a previous job, we had an application that was over 10 years old and there was a bunch of views defined. So you get somebody maybe embedding quite complicated logic inside a view. And then years later, maybe another developer would come along and they would need to create another view, but they would find some logic they could reuse from the original view, but there was some column missing. So then you hit a dilemma. Do you modify the original view and add the column that you need and risk maybe breaking things that do select star from that view? Or do you just join a table again in your view and call it done? But the problem with the second part, like the latter one, would be you're joining the same table twice, and effectively that's a waste of effort. So this commit helps with that. So the next change I want to talk about, effectively, this improves set operations in Postgres 18. And set operations are like unions, accepts, and intersects. union is the most common set operation, I would say. Except and intersect are less common, but they do exist. And this particular change affects only except and intersect. So let's look at an example of what's actually changed here. So I've deviated from the parts table slightly, and I have a table A and a table B, which I'm going to insert 1 million records into each of those. I'm going to run analyze to gather some statistics so that the planner can make some informed decisions about how to execute this. And then I'm going to run select star from A, except select star from B. So basically, give me all the records in A, subtracting all the records, matching records from B. And let's look at how that has been executed. So on the top box with Postgres 17, I think the biggest thing to pay attention to is probably the execution time here. And for Postgres 17, that's 354 milliseconds. And for Postgres 18, it was about twice as fast. And there's a few details here that are quite interesting with Postgres 17. You can see that it sequentially scans both tables at the bottom of the Postgres 17 box. And then there's a subquery scan. And that subquery scan doesn't exist in the 18 version. And the reason that that doesn't exist is this worked quite strangely until this changed. Postgres 17 would add a little flag, a 0 or a 1 to either side of the except, so that it could later identify where it came from. And to do that effectively requires a projection step. And that's why the subquery scan exists in 17. And the planner is effectively able to eliminate that in Postgres 18 because the target lists are effectively the same. There's no effectively junk columns that need to be removed before it's actually output to the client. And one thing to note about the Postgres 17 is effectively, if you look further up at the append, that's effectively concatenating both sets of results. So mixing them all together effectively, and then it's sorting it. And it sorts it by the entire select list plus that flag at the end. That flag becomes the 0 or 1, effectively becomes a tiebreaker. And then that's fed into the set operation, and that looks at that flag to figure out which side it came from. And this feels like very old design in Postgres, because we have means to identify where the row came from by other means, because we have things like joins that have an outer and inner side. So Tom has modified this to effectively use that modern infrastructure. And what that allows us to do is it allows us to use pre-sorted input. In this case, I've got an index to allow that the records to be obtained already in sorted order, and just feed those directly into the set operation. And for this particular scenario, that's doubled the performance of this query. So the next change I want to talk about, I committed this one. I wasn't the primary author. But basically, Postgres has had the ability to remove redundant group by columns using primary key indexes for quite a long time. And what that allows, why that can happen is effectively if you have a group by clause that contains the primary key and then some additional columns from the same table, because the primary key is guaranteed to be unique, having those additional columns in the group by clause doesn't make it any more unique. So effectively, we can just silently get rid of those and return the same results. So this change effectively expands on that to allow the same to work for unique indexes. And there is a couple of things that need to be met before that can be allowed. So there has to be a not null constraint on the column that is in the unique index. Expression indexes won't work because we can't have a not null constraint on an expression index. If there's no not null constraint, then the index needs to be defined as nulls, not distinct. And that means there can only be a single null value rather than multiple. So ordinarily, the uniqueness is not enforced for nulls, but nulls not distinct changes that to allow that to be distinct. And if we just look at an example, parts table is back, and I've got a unique constraint on the part code. And I've introduced a sales table just so we can actually do something a bit more meaningful with this query. Sales table just has a part ID, the same as the parts table. So that's going to be our join condition. And the query I'm going to run is just an aggregate query. I want to know say this is run at the end of the month. We want to look at the total sales for some period of time. We want to group by the part code, and we want to take the sum of the quantities sold. So you can see here that because you can't memorize, or I can't memorize all the part codes, we need some meaningful description. I have added the part description to the select list. And because I did that, I had to also add it to the group by clause. Otherwise, Postgres would complain that I'm missing a column from the group by clause. And if we look at the actual explain output from both, you can see that on the left, Postgres 17 has got both those columns in the group by clause, whereas in Postgres 18, it's eliminated the additional column, that part description, from the group by. So I think that's probably, it's going to be quite useful there. This is a hash aggregate, so effectively it's going to be much cheaper to obtain that hash value when the executor is building that hash table. And also, you can imagine that the part description is much longer than the part code, so it's going to be quite a lot cheaper to actually only group by that single column. So now I want to move on to part 2, and this is general query planner performance improvements that have happened in Postgres 18. So let's have a look at what's happened here. So Thomas has made a change here, and the top line of the commit message is increased number of fast path locking slots. So what does that mean? So whenever we do anything in Postgres, we have to obtain a lock on the object that we're going to use. So if you're running a select query on a table, we must obtain a lock on that table. And that prevents things like other concurrent sessions from doing a drop table or some other operation that conflicts effectively with what we're doing. So that ordinary locks have to be coordinated between all backends, but for certain sort of lower strength locks, like the strength of lock you would take to do a select, they're eligible to be fast path locks. And what that means is we don't have to go to this shared location that coordinates between all backends. It can go to a local location and check that we can lock that. And what that actually allows is, well, basically that gives you, up until now, there's been 16 slots for those fast path locking slots. And with partitioning workloads, you could quickly run out. 16 partitions isn't a huge number. So if you had, 24 partitions, then you would quickly fill up. You consume all those 16 locking slots, and subsequent locks would need to spill out into that shared lock table. So if we look at the performance of this here, what I've measured is I've created 2 partition tables, one with 16 partitions and one with 32 partitions. And I'm just doing these tables are empty. So what I want to measure here is just the overheads of obtaining these locks at executor startup. So you can see that Postgres 17, and by the way, if you're struggling with the colors, the bars in the graph are in the same order as they are in the legend at the top of the graph. So you can see on the left, we've got Postgres 17 with 16 partitions. And up until, once you hit 32 concurrent running sessions running this particular query, you can see that Postgres 17 starts to slow down. And by the time I get to 64 concurrent sessions, it's really starting to slow down. And if you look at the next bar to the right, and that's the 32 partition case, it's much worse. And the thing, even with the 16 partition test, we obtain locks on 16 partitions, but there's also the partition table itself. And we have to obtain the lock on that partition table as well. So there's actually 17 locks there. So in the 16 partition test, there's actually 17 locks, and that's causing even that one lock that spills over into that shared lock table. is starting to cause sort of contention at that common point that all these sessions are touching. If you look at Postgres 18, this is the blue bars, things are much better. The scalability is much more linear as we increase the connections. So this change that Amit committed, this effectively changes the order of operations for runtime partition pruning. So when the query planner is unable to do partition pruning, it's possible that if if the value being compared to the partition key is maybe a parameter that comes through a prepared statement, or if it's a result of a stable function, then the planner doesn't have access to see what that value is at plan time, but the executor will. So we can defer that partition pruning until execution. But the problem with that is the planner still has to generate a plan with every possible partition that could match. And then it's up to the executor to prune the ones away that don't match the value being looked at. But the problem was the order of operations. So always when we start up during execution startup, we have to obtain locks on every table that we're going to look at during execution of that query. But the problem was we're taking those locks before we did that runtime partition pruning. So if you had, for example, 1,000 partitions in a plan and you pruned all but one of those during execution, we'd still take 1,000 locks. That's now changed. We now do the runtime partition pruning before obtaining the locks on the partition. And that improves things fairly massively. And we can see here, along the bottom, I started at one partition and I'm just doubling that each time until I get to 8,000 partitions. And you can quickly see that the Postgres 17 doesn't scale well. And just keep in mind the unit of measure here is in microseconds. So this isn't a large amount of time. Even for the 8,000 partition case, Postgres 17 took 1.8 milliseconds. So it wasn't slow. So this really only affected things if the query you were running was very fast to execute. If the query had taken several minutes to execute because it was looking at lots of data, you wouldn't really have noticed this. It's really only for fast to execute queries. But the more partitions you have, the more you're probably going to benefit from this change. If we look at the scalability for the Postgres 18, then it's fairly linear. There's sort of a very small slowdown as we get to higher partition counts. And I've actually identified what that is, and I do have an actual patch pending, which I might submit to Postgres 19, which maybe we can fix that. But it's sort of diminishing returns now because the bulk of the problem has been solved by this change. So another planner improvement that has been done in Postgres 18, and Yuya Watari has been working on this for quite a number of years now, and that patch went through multiple evolutions and design, and it's finally landed for Postgres 18. And this improves internally in the planner. We have these things called equivalence classes, and those define that basically for any given row, they record where two columns are equal to each other. What that allows is things like if you have a query that's, say, select star from table where column A equals column B, then you have an order by clause to say order by column A. Then the query planner knows that that is equivalent to order by column B, and that allows a bit more flexibility. So you have an index on column B, then it can use that index to provide pre-sorted input for that order by clause. So this change effectively, the problem was that with partitioned workloads, the number of members, i.e. the number of columns that are defined as equivalent within those equivalence classes, when you have partitions, it would always add another member for every partition. And that caused problems. If you have thousands of partitions, and we could end up with thousands of these equivalence members. And the problem was the actual internally within the planner, when searching for those, it was a linear search. So that search would become slower and slower the more partitions that were added. But also the more partitions that were added, the more number of searches that we had to do. So effectively that caused a quadratic slowdown. And this commit fixes that problem. And if we look at the performance, again, I've got started at one partition here. I'm doubling that each time. I didn't go to the full 8,000. I only went to 1,024. And the reason for that was because the performance difference was very large with, it was 9 times faster with 8,000 partitions, sorry. So with 1,024, it was twice as fast to plan this. So this is only query planning time to plan this query with that number of partitions. So this is fairly significant. It's been a known problem for quite a while in Postgres, and hopefully this is going to solve that. So certainly those changes are not the only changes to the Postgres query planner. I just had to pick some, and there is other changes here. Like for example, Windows users, work mem used to be limited to 2 gigabytes, and that restriction has been lifted. 2 gigabytes is not a very significant amount of memory these days. And this other stuff, there's select distinct queries are now able to sort of internally reorder the columns in the distinct list. There's no visible change in the output, but that allows indexes to be used that previously weren't considered. So now is probably a good time if you have a test environment and you're thinking of upgrading to Postgres 18. Then try these out. Like there should be beta 1 or beta 2 should be out by the time you watch this. And there's a link there if you want to get in and test. The earlier we can identify problems with these features, the better. The less chance we've got of finding something late on before we release and possibly having to delay the release. So I'd encourage you all to get testing and give us some feedback, good or bad. It's all welcome. So now I should be lurking. Future me should be in the chat somewhere, and I'm happy to answer any questions anybody has.